All right, we're going to look at 13.5, which is colligative properties. Colligative properties, first and foremost, are properties that depend on concentration or a collection or quantity of particles, which is why they're called colligative. Okay, they depend on the amount of your solute particles. These properties change depending on how much of your solute you have. There are 4 of them. They are freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. So you have 4 colligative properties: freezing point, boiling point, vapor pressure, and osmotic pressure. 4 properties that change when your amount or concentration changes. All right, the first one we're going to talk about is lowering your vapor pressure. So vapor pressure is the first property we're looking at here. Now you have a volatile versus a non-volatile substance. Volatile substances are those that become a vapor very easily and will exert a vapor pressure, while non-volatile exerts no measurable vapor pressure and just instead gets in the way of the volatile substance becoming a vapor. So when we look at the example here to the right, okay, if you just have your solvent alone, if we add a non-volatile solute to it, which is the ones in the red here, okay, all they do is they just get in the way of the blue ones here, my other solute or solvent, trying to evaporate or vaporize. So that's a volatile, which easily vaporizes, and a non-volatile, which doesn't, and then just gets in the way. Okay, we have what's called Raoult's law, and this quantifies the extent to which a non-volatile solute lowers my vapor pressure. And when we talk about lowering that vapor pressure, it's because, again, my solute is getting in the way and doesn't allow those solvent particles to evaporate. So by how much? Well, we have our pressure with the solute is going to be equal to our mole fraction, and it's the mole fraction of my solvent, okay, times the vapor pressure of my pure solvent. All right, so how this works then, okay, it says, again, your mole fraction is how many particles there are in the solvent. Okay, the more particles of my solute I have in there, the more they get in the way and the less my solvent evaporates. So if I have a lot of solvent and not much solute, okay, maybe 90% solvent, then the pure isn't going to change very much because I'm going to have 90% of what it's supposed to be by itself. But if I have a very small amount of solvent, then my pure solvent vapor pressure is going to go down even more than what it was before. And that's what it says here. Vapor pressure goes down, depends only on the amount and not the kind. So if I have 85% of my solution being solvent, then the pure is not going to change very much. But it doesn't matter anywhere in here exactly what it is. All I care about is how much is there. When we look at now a practice problem, we have glycerin. It's a non-volatile, non-electrolyte, has a density there. We want to calculate the vapor pressure of a 25-degree solution made by adding 50 milliliters of glycerin to 500 milliliters of water. We have less glycerin, which is why the mass is solute. Water is my solvent. They give you the vapor pressure of water at that temperature, and they give you the density of water. Okay, so I want to calculate, again, the vapor pressure at 25 degrees of my solution. I eventually, this lovely equation we looked at a second ago, okay, this P on the left side is my solution, so on the right is my solvent. So I eventually want this one on the left there. Okay, well, what do I need to know? I need to know a mole fraction, and nowhere in there do they directly give me moles. So I've got to do a little bit of work here. Okay, and then I can plug it in. Well, I want my moles of glycerin, okay, because I'm going to need that. Well, it tells me that I have 50 milliliters of glycerin, and it gives me the density of glycerin. Density, remember, is mass divided by volume. So if I want a mass to eventually get a moles, all I do is take my density times my volume. So times 1.26 grams per milliliter. And I'm going to get 63 grams. Well, I need moles. I take my grams divided by my molar mass. I add up C3H8O3, and I'm going to get 92.1 grams per mole. So we divide by 92.1. And I'm going to come out here with 0.684 moles. Do the same thing now for our water. They tell me that I have 500 milliliters times 1. Well, that's really easy. Okay, obviously that's 500. We have 500 grams divided by the molar mass of water, which is 18.02. And I'm going to get out here 27.5 0.8 moles of water, which is very apparent that the glycerin is definitely my solute. Okay, well, I take this mole fraction times the pure pressure of my solvent, which they told me here is 23.8. Okay, so I'm going to figure out my solution by taking my pure solution equal to my mole fraction, okay, and I have to add them together. Now the question becomes a lot of times what number here goes on the top. Well, I need to know what fraction or what percentage of my solvent is actually still there, creating that original or pure pressure, or compared to that pure pressure. So we take the 27.8 moles on the top. It's always your solvent times the pure pressure here, which is 23.8 torrs. We divide here these two, we multiply, and we should get 23.2 torrs, which makes sense because you have mostly solvent particles here. 27.8, and we're going to add to that 0.6. You're not adding a whole lot. So my vapor pressure is going to lower, but not going to lower very much. Really, it's like 97% still the original water. So let's look now at ideal solutions. Okay, real solutions behave ideally when your solute concentration is low, or my solute and solvent particles are similar in size, or if they have similar intermolecular forces. Remember we talked about real gases and ideal gases? Same thing here with solutions. Okay, if your solute concentration is low, then it's going to be just like we had in the previous problem. We're going to have like 97-98% of the solution is actually still the solvent. So my vapor pressure is not going to change very much. All right. Now, if they're similar in size or have similar intermolecular forces, now you're talking about, okay, you're not interfering a lot, or they're not interfering a lot differently. They don't have really huge particles that are getting in the way and causing us to care a little more about what kind they are. Okay. Now, when is Raoult's law not really going to be good? Okay. That's my intermolecular forces or my solute solvent are weaker than what they would be by themselves. Okay. My vapor pressure tends to be higher then, and the solute solvent don't bond, and they get in the way of the solvent vaporizing. So oppositely, when your solute solvent are really, really strong, meaning they don't want to vaporize at all, then I have really low vapor pressure. So it takes a lot of energy to break apart my solute solvent bonds. Okay? So if I have really weak attractions between the solute and the solvent, now it's really easy to get rid of them. I'm going to have a really high vapor pressure, and my solute's barely getting in the way. Okay, I'm just going to throw off a little bit there on exactly how much that amount of solute changes your actual vapor pressure. Okay, now along the lines of vapor pressure, we're going to look at boiling point elevation. Okay, so that's the next thing here. Okay, we're look at our phase diagram a little bit here. So since our vapor pressure is going to go way down when we have a solute in a pure solvent, my vapor pressure line kind of goes down or shifts downward. Okay? And I'm going to kind of explain, and then we're going to look at a picture. Okay? So my normal boiling point, okay, it says, why is it raised for a solution? Now since your vapor pressure lowers, it's going to be less than 1 atmosphere at its normal boiling point. Okay, water is normally 100 degrees. And a higher temperature is then going to be required to reach the vapor pressure of 1 atmosphere, so that it's going to boil. So let's take a look here at the picture of a phase diagram. All right, so normally, okay, and the dark black line here, okay, I have my 1 atmosphere. That's when water is going to boil. So it's my normal boiling point. All right, but, okay, when I have a solution, now my vapor pressure is going to go way down. So at the normal 100 degrees, which is right here, okay, at my normal 100 degrees Celsius, I don't quite have the vapor pressure that I used to. Because those solute particles are getting in the way. So now when my water is 100 degrees, I'm not really at my boiling point yet. So what happens is you have to add more heat, okay, in there to get my vapor pressure to go back up, to get more of those particles out and creating pressure over top of my liquid. And so now, at 1 atmosphere, it takes a lot more degrees, and I think it's around 110. Okay, or we'll just say 110 degrees. So now it'll take me 110 degrees or an extra 10 degrees for this part right here where I have to break those bonds more and give more vapor pressure at that particular 1 atmosphere now. So notice how it's kind of shifted downward. Okay, a pure liquid solvent versus a solution. The blue line here is a solution. All right, that's water in particular here, and then anything dissolved in the water. All right, and we have on the chart here, okay, and on yours, you see kind of a delta T with a B. And what that means is that's my change in temperature for boiling. All right, so if we go back now and look, okay, we have a vapor pressure or a boiling point elevation equation. And delta TB is equal to KB, which is a constant for a solvent, times my molality of my solute. It's a molality, not a molarity. Because we're dealing with changing in temperature here, so we can't do molarity. Okay. Now we're going to look at the difference between like sucrose and table salt when we add these for boiling points. Okay. When we have sugar, okay, here's an example of sugar, C6H12O6. When it's bonded to another sugar, if I have 1 mole of it, 1 mole will dissolve. All we're doing is breaking the intermolecular forces in between 2 sugars. Now, if we look at salt, okay, salt when it breaks apart in water and dissolves in water, breaks apart everything. Not just the Na and the Cl from an NaCl molecule, but actually the Na and the Cl itself, that ionic bond in between the two. So if I have 1 mole of salt to start, I'm going to actually form 2 moles of ions, which means I'm going to have twice the amount of solute getting in the way of that solvent, which means I have 2 times of the higher of a boiling point. The more ions you have in the way, the more higher it's going to make that boiling point. Or on the flip side, the lower we're going to have that vapor pressure. Okay, and you see these constants that are here. Okay, and it changes based on whichever one you have. Okay, so keep that in mind when you're looking at exactly what it is. You do care a little bit about what it is based on how much the boiling point is going to increase or how much the vapor pressure is going to go down. So let's look at freezing point depression, and then we're going to do some examples. When we look at this, is which one freezes first? Well, pure solvent crystals freeze first. Okay, your solid particles are not soluble in the solvent when it's a solid. So the pure stuff will start to crystallize first. All right, which means how is our phase diagram affected? Well, my solution will start to freeze sooner at a lower temperature. So the solid liquid and liquid gas lines meet at a lower temperature or a lower triple point. Okay, lower vapor pressure, so the triple point is lower. All right, now your solid liquid line rises vertically from your triple point. So since the triple is lower, my solid liquid line is lower. And so let's take a look at this picture. So again, notice how this has shifted downward from the pure to the solution. Okay? And that all has to do with a lower vapor pressure. I have a lower vapor pressure, which means now this triple point is going to happen a lot lower, where it actually meets my gas line or my solid line. Okay? So since it makes sense here that this has to rise vertically from my triple point, so now my solid liquid line is going to be a lot lower, which here is my normal melting point. Now here's my solution's melting point, okay, at 1 atmosphere. You want to think about this now when we look at these freezing point and melting point lines. If the solvent first starts to crystallize, that's my freezing point. Now the decrease in my freezing point is actually the freezing point of my solution minus the freezing point of the solvent. And we have another equation that looks very, very similar, okay, to the boiling point elevation. So you decrease the freezing point, and again, M is molality, and Kf is the freezing point depression constant for the solvent. Again, it's for the solvent. You're going to think about road salt. Okay, that is calcium chloride most times, and what that does is that lowers the freezing point of water, of ice, makes the road slushy. So instead of freezing at this temperature, okay, with water at 0. Now we add salt to it. Now the salt's going to lower that freezing point, and now water's going to melt at, or freeze at, -10 degrees, or whatever, depending on how much you have in there. Okay, so let's look then at a couple practice problems. Okay, it says automotive antifreeze consists of ethylene glycol. It's a non-volatile, non-electrolyte. Calculate the freezing point and boiling point of that mass percent of solution of ethylene glycol in water. Well, that mass percent, all right, means that I will have 25 grams of this antifreeze, or my ethylene glycol, and the rest of it, the 75 grams, is going to be water. And at both of these, boiling point and freezing points, I need to know my molality. Okay, well, we think back to what molality is. It's always molality of my solvent for both of these. Well, it's moles of solute per kilograms of solvent. So, take my 25 grams of my solute, we divide by my molar mass of ethylene glycol, add all those C's, H's, and O's up, we get 62.1. Divide by kilograms of solvent, and we get a molality of 5.37. All right. Now, if I want to look at my boiling point temperature and how much that's going to go up, okay, I take my constant for the solvent. We look at that chart. You find water. Water is 0.51 degrees Celsius per molal. How many molals do I have? I have 5.37 molal, which means then my boiling point is going to go up by 2.7 degrees. Now, does that mean the boiling point of water is 2.7 degrees? No. It means you add it then to what it is normally. So it's going to now boil at 102.7 degrees Celsius. Again, that's why they tend to add salt to like pasta water, spaghetti water, makes the boiling point go up. Now, temperature for my freezing point, okay, same molality, but it's a different constant now. This one is 1.86 degrees Celsius per molal in that chart. We have 5.37 molal. We're going to get, as an answer here, -10 degrees Celsius. Okay, now when does water actually freeze? It freezes at 0, so -10 degrees Celsius is now when that solution is going to freeze. Another one here, it says list the following aqueous solutions in order of their expected freezing point, and they have named molalities and what they are. So remember, looking at the highest molality, because that means I'm going to have the most of my solute, but you've also got to look at the amount of ions. If you have more ions, you're going to have a higher molality. So, you got to know what kind of bonds you've got going on, okay? So I got a 0.05 molal CaCl2. How many ions is that going to break apart into? Well, it's going to break apart into 3. 1 calcium and 2 chlorines. It's an ionic bond, so everything splits apart. So we actually have 0.05 times 3, which is going to be actually 0.15 molal. Okay, what about 0.15 molal of NaCl? Well, that breaks apart in a solution with water. It's going to break apart both of them, so I've got 0.15 times 2, which is 0.30 molal. Okay, HCl has a molal at 0.10. HCl is also a kind of ionic bond. It's actually an acid, okay, and later on in the chapter we'll look at this one versus this one. Those are both actually acids. One of them is a strong acid, one of them is a weak acid. So you may not know this yet, but we're going to learn it right now in the next chapter as well. HCl is actually a strong acid, so it's going to totally break apart just like an ionic bond, so you have 0.10 times 2. And again, I would not expect you to know that right now. This is kind of like integrating the next chapter here. So, like I said, this is actually a weak acid, so it's a little bit weird, okay, and how this is going to work, but I'm going to kind of explain it here. What's going to happen is, with weak acids, sometimes they split, and sometimes they don't split. So you actually end up with a kind of in-between amount of between 0.10 to anywhere to 0.05 molal. Because some of the acid breaks apart, some of the acid doesn't break apart. That's a whole set of chapters into exactly how much breaks apart. Okay, and then lastly we have a type of sugar. Okay, notice how they're all covalent bonds. So none of that's going to break apart, so we're going to have 0.10. So list them in order of their expected freezing points. Well, the lowest freezing point is NaCl, next HCl, followed by CaCl2, followed by the sugar, and then lastly acetic acid. All right, last one we're going to look at here is osmotic pressure. Okay, osmosis is a semi-permeable membrane that permits passage of some components of a solution. They often permit passage of water, but not larger molecules or ions. These are like cell membranes or cellophane. They let some things through, but not everything through. Okay, osmosis then is the net movement of my solvent, usually for us that's water, from an area of low solute concentration to high solute concentration. It's trying to balance out these solute concentrations. Okay, you consider a U-shaped tube with two liquids separated by one of these membranes. One of them is a pure solvent, one of them is a solution. Okay, there is going to be a net movement of solution in both directions. Okay, and my concentration of solvent is higher in the solution containing less solute. So the rate with which solvent passes from my less concentrated to my more concentrated is greater than the rate in the opposite, meaning it's going to flow to the side where there's more solute to try and even out the two sides. Okay, so there is a net movement from my less concentrated side or solution into the more concentrated solution. Okay, so here I have a more concentrated side and a less concentrated side, and water is the blue one. So the water is going to move over here to try and balance out all of these extra solute particles and make the two the same. Okay, that's osmosis, and you have a whole picture there on your notes as to how osmosis works. Well, the osmotic pressure part, okay, and since it says since there's a net movement from right to left, the two liquid levels in the arms become unequal, and the pressure difference in the unequal heights becomes so large that the net flow stops. And you can kind of apply what we call an osmotic pressure to prevent osmosis. You'd have to apply this pressure to get the sides to go back the way they were. That's an osmotic pressure. Okay, that's all we get into with that. We don't get into the math, how you calculate it or anything like that. Just know that depending on how many particles you have on each side, depends on how much that solvent moves. When the solvent, or water in our case, moves, now we've got unequal sides, we can push them down, and that's that pressure that can change based on how much we have and how much of that solvent moves.